This is my presentation for test number 4 in Calculus 2. Number 1 asks us to complete the following regarding Taylor polynomials. Part A is find the nth order Taylor polynomial of the function f of x equals 1 divided by the square root of 1 plus x centered at 0 for n is equal to 0, 1, and 2. Alright, so I'll start by stating the function f of x is equal to 1 divided by the square root of 1 plus x. I'll rewrite the function 1 plus x to the power of negative 1/2, and then I'll calculate the derivatives of the function. The first derivative is negative 1/2 quantity 1 plus x to the power of negative 3/2. The second derivative is 3/4 quantity 1 plus x to the power of negative 5/2. I mention here that the Taylor series or Taylor polynomial is centered at 0, so a is equal to 0, and so therefore the 0th order Taylor polynomial for f of x, p naught of x is equal to 1. It's a constant 1. The first order Taylor polynomial, p sub 1 of x is equal to quantity 1 minus 1/2 x. The second order Taylor polynomial, p sub 2 of x is equal to 1 minus 1/2 x plus 3/8 x squared. Part B asks us to graph the Taylor polynomials in the function. The function is graphed here. Starts here, there's an asymptote at x is equal to negative 1. It continues here, decreasing, always approaching f of x is equal to 0 as x goes to infinity. The first order Taylor polynomial, or sorry, the 0th order Taylor polynomial is a flat line. Here, its slope is 0 constantly. Its p sub naught of x is equal to 1. Have it labeled there. The first order Taylor polynomial is a line that lies tangent to the curve at the point 0, 1. That's this line here, p sub 1 of x. The second order Taylor polynomial is a parabola that lies tangent to the curve at the same point. Here underneath the function, passing through this point, and then above the function, labeled p sub 2 of x. Part C asks use p sub 2 to approximate the value of 1 divided by the square root of 1.08. I'll write that real quick here and say that it's equal to f of 0.08, given that 1 plus 0.08 gives us 1.08 from this function here. And then I'll continue to evaluate p sub 2 of 0.08. That's equal to 1 minus 1/2 quantity 0.08 plus 3/8 quantity 0.08 squared, which is equal to 0.9264. The absolute error in this approximation, given that the function value at 0.08 is given by a calculator, is f of 0.08 minus p sub 2 of 0.08 is equal to 1.4955 times 10 to the negative 4th. Okay, question number 2 asks us to determine the radius of convergence for the power series expressed by the summation of x divided by 3 all to the power of k. Then express the endpoints, or test the endpoints to determine the interval of convergence. So number 2, the first step I take in determining the radius of convergence is I substitute r in the place of x divided by 3 and rewrite the series, the summation of r to the power of k. And I do this because now it represents a geometric series, so by the properties of a geometric series, the series converges if the absolute value of r is less than 1. So substituting x minus 3 in the place of r now, or x divided by 3 in the place of r, you see the absolute value of x divided by 3 is less than 1, and the absolute value of x is less than 3, making the radius of convergence, capital R, is equal to 3. It follows that since the geometric series, or since the series can be expressed as a geometric series, there is the series does not converge at the endpoints, because the geometric series must have a common ratio that's absolute value is less than 1. So the interval of convergence is negative 3 is less than x is less than 3. Alright, Number 3 asks find the first 4 non-zero terms of the Taylor series for the function f of x equals 1 divided by x centered at 2. Then write the power series using summation notation. Okay, so the first thing I do in calculating the first 4 non-zero terms is I mention real quick that the nth term of a Taylor series is equal to f to the power, or the nth order derivative of f of a times quantity x minus a to the power of n divided by n factorial. Here we're going to start at n is equal to 0. That'll be our first term. So I follow by calculating the derivatives of f. F prime of x is equal to negative x to the power of negative 2. F double prime of x is equal to 2x to the power of negative 3. F triple prime of x is equal to negative 6x to the power of negative 4. A is equal to 2, indicating our Taylor series is centered at 2. A sub naught of x is our first non-zero term, and that's basically f of 2, which is 1/2. Our second non-zero term in the Taylor series is negative quantity x minus 2 divided by 4. Our third non-zero term is quantity x minus 2 to the power of 2 divided by 8. And our fourth non-zero term is negative quantity x minus 2 cubed divided by 16. Alright, that concludes part A, the first part. The second part asks us to write the power series using summation notation. I observe here that for each term, the consecutive term has an alternating sign. So our first term is positive, our second term is negative, our third term is positive, and our fourth term is negative. So I put this in parentheses negative 1 to the power of k minus 1 because that's going to give us that alternating sign pattern where our first term, when k is 1, is positive, because 1 minus 1 is 0, negative 1 to the power of 0 is 1. Each term after that, each consecutive term will have an alternating sign. Alright, the second thing I notice is that we have a factor in the numerator of quantity x minus 2 to the power of k minus 1. Here, when k is 1, that's 1 minus 1, and x minus 2 quantity to the power of 0 is 1. Here it is to the power of 1, here it is to the power of 2, and here it is to the power of 3. The last bit that I noticed was that we have terms of the geometric series 2 to the power of k in the denominator. So this is 2 to the power of 1, 2 to the power of 2, 2 to the power of 3, and 2 to the power of 4. So I wrote 2 to the power of k in the denominator. All in all, I've stated that our function, 1 divided by x, is equal to the summation of, as k goes from 1 to infinity, of that guy right there, that monomial. Alright. Number 4 says let x of t equal t minus sine t and let y of t equal 1 minus cosine t. Part A asks us to determine dy dx in terms of t and evaluate it at t is equal to pi over 4. So the first thing I'll note is that the derivatives with respect of t to our components of our parametric equation are x prime of t is equal to 1 minus cosine t, y prime of t is equal to sine t. dy dx can also be written in the notation form y prime of t divided by x prime of t. And here I stated outright the way I've calculated those derivatives with respect to t, sine of t divided by 1 minus cosine t. I use some algebra, multiplying by the conjugate of the base in the denominator and the numerator to get it in a more familiar form. This is a Pythagorean identity, so that's sine squared of t. A sine of t can be canceled out in the numerator and the denominator, so you're left with 1 plus cosine of t divided by sine t, which is cosecant of t plus cotangent of t. I felt like this is the simplest form to express that answer in. For the second part of part A, they ask us to calculate dy dx at t is equal to pi over 4, so I've written it in this notation, again, y prime of pi over 4 divided by x prime of pi over 4, and I just sub in pi over 4 over here, and that gives us square root of 2 plus 1. Alright, part B asks us to graph or make a sketch of the curve showing the tangent line at the point corresponding to the given value of t. So here's our parametric curve here, as t is an element of 0 to 2 pi. I've decided to give arbitrarily. I have it oriented this way. I believe it actually also goes back the opposite direction after t is equal to pi. I should probably written that in. But anyway, our tangent line, the slope of our tangent line at t is equal to pi over 4 is given here. That's negative root 2 plus 1. So I took the inverse tangent of this, and it output 67.5 degrees. Took a protractor and lined an angle of 67.5 degrees from horizontal to be tangent to this curve at one point the best I could. And that's part B.